Welcome to this kind of wrap-up lecture. I just want to wrap up the chapter on momentum. So we talked about reformatting Newton's laws into being in terms of impulses changing momentum, different way of looking at Newton's second law. And Newton's first and third laws can be reframed as conservation of momentum, right? Just, as long as you don't have any external forces, then the total momentum in your system will be the same before and after any interactions. So that's what we talked about before. So I just want to define a little more cleanly some terms we've been batting around, and that is this idea that collisions can come in two flavors, elastic and inelastic. So just to be clear, right, if you have a collision, the momentum is always the same before and after, right? I mean, there may be, if you might have to go to the instant before to the instant after to avoid the effects of friction or other external forces, but in principle, the momentum is the same, regardless of how the collision goes down, right? Like, it doesn't matter if they stick together, if they bounce off at right angles, right? As long as you do the vector math correctly, the total momentum should be the same before and after. What is interesting, though, is when you look at it through the energy lens, okay? So classically, most collisions are going to involve some loss of kinetic energy, and that's because collisions are messy, right? Work gets done, and that objects get deformed slightly, noise is generated, heat is generated, right? And so that broad category of collisions where kinetic energy is not conserved, which is the common case, those are known as inelastic collisions, as in not elastic. On the other hand, if you can have a very clean collision type where the things bounce off of each other and they don't interact very much during the collision and no heat is generated or a negligible amount, and you can, the kinetic energy is close enough to being conserved, then you would describe that as an elastic collision, as in you get everything back, right? It bounces back. And so that gives you a third equation, basically, right? Because you've got momentum in the x direction being conserved, giving you one equation, momentum in the y direction being conserved gives you a second equation. And now if you're told it's elastic in nature, then you can say the 1/2 mv squareds in the beginning are equal to the 1/2 mv squareds in the end, okay? And then there's one sort of third, like a keyword, like a coded word. If a collision is described as being completely inelastic, right? That means not only is it messy, but they completely stick together, actually, right? And so that they don't even have to show you the after picture of the collision. You know that the two masses or three masses or whatever type of collision it is, they're all stuck together, and then they move as one large mass afterwards. Okay, so kind of no new physics here, just a clarification about the nature of collisions, right? Momentum always conserved, kinetic energy usually not, usually lost, but in a very clean collision. And, it's not always just an approximation to say a collision is elastic. You can have objects that interact without touching. So, for instance, one electron bouncing off of another electron, they're never going to get close enough to actually have any frictional forces or anything like that, right? Or a gravitational slingshot effect where an asteroid is pulled off of its course by the gravity of a planet or something like that. That is an interaction that can involve an exchange of momentum. It's not a collision as you think of it normally, but it can be modeled that way. And those can be 100% elastic, right? Okay, the other thing I want to talk to you about today, one other thing, one other kind of detail. So normally when you get that third equation where you have an elastic collision, it's mathematically more difficult because the v is squared, right? So you got the 1/2 mv squared, and so it's got the v sub x and the v sub y in there. And sometimes it makes for messy math. So it is worthy to note, and you can look at the algebraic derivation of this on page 176 in the textbook, that there is a special case when you have a 1D, two-object, completely elastic collision, then because the KE and the PE is conserved and it's only one dimension, you can see that the relative velocity before and after is the same. The relative velocity maybe not technically because I think there's a sign difference, like a plus to minus sign or something. So you can say the relative speed is the same before and after. And that could be a useful shortcut, right? So for instance, if you just look at this, I drew this on the board, like any M1 having a head-on collision with any M2, so I just made up some numbers here. Let's say M1 is going at M2 at 35 meters per second, and M2 is traveling at 5 meters per second. And if I tell you their collision is 100% elastic, then and it stays in that one dimension, then without knowing the masses or any details about afterwards, it's hard to say anything specific. But you can say that the relative speed of M1 and M2 after the collision must be 40 meters per second. The difference in speeds must come out to be 40, because that's their relative velocity beforehand, right? 35 head-on collision with 5 gives you a relative velocity of 40. Okay, just wanted to show you that trick because it's not new physics or anything, right? It just saves you on some math, potentially, in that rare case. All right, then the last part of the chapter, he talks about center of mass. So let's define the center of mass and talk about how you find it mathematically and talk about why it's a useful concept, right? So remember when we did free body diagrams, I was always joking, like, it doesn't matter what the object really looks like, just represent it as a dot, and then draw the arrows coming out of that dot, right? So when you do sort of shrink an object down and you're representing it by a point, what point physically does it make sense to do? And that point that we're imagining is basically the center of mass. That is it's the weighted average, if you will, of the location of all the mass, the distribution of mass in the object, right? So real world objects exist in 3 dimensions and have masses at various locations, right? But when we reduce it to a single point, what point does it make sense? Like if you're talking about a person, should it be located where their head is or where their feet is? And the answer is, from a physics sense, the point that makes the most sense, not knowing anything else, is the center of mass, which is somewhere near your belly button. And the center of mass, of course, is also the object, like when you talk about something following a parabola, when you throw it through the air, you get parabolic motion, or when you do kinematics and you're describing the acceleration and velocity, once again, if you have distribution of mass, like you imagine your whole body when you're running or something, different points on your body may be moving in different directions, like you're pumping your arms when you run and like your right leg is going forward before your left leg. And so it's really messy to describe all the details. But when we're using kinematics and we're describing the acceleration, the velocity, instantaneous of the center of mass of the object, right? So how do we find it? So here's how you find a weighted average. This formula should look familiar to you, right? If you want to find the weighted average of something, what you do is you add up all the terms. So that's the summation symbol here. N is the number of pieces that you have in your system. And each mass, individual location in your body, for instance, or whatever object you want to do, has a mass at that location. And you would use the x position of that individual mass. And so you're weighting the x value with the mass at that location, and then you sum all of the locations that have mass at them, and then you divide by the total mass. That's what the capital M is, right? And that's just how you find the weighted average of anything. And then, if it's a 2-dimensional problem, then you have to do it again in y. And of course, in the real world, you'd have a third equation and do the weighted average in z to find your center of mass x, y, z. Right, so there'll be a couple of practice problems. Nothing as complicated as doing it for the human body, right? I don't think I have anything else to say about this. So now, the center of mass of the total system is pretty useful if you think about conservation of momentum, right? So if you can have pieces and parts that are moving around and exchanging momentum or applying forces within the system. But if you can find the center of mass of an entire system on which there are no external forces, then the center of mass of that system has to obey Newton's laws, right? So for instance, if you have a boat with 2 people on it and the people are walking around, they'll be exchanging forces between their feet and the boat, and then they may actually exchange forces between them. But those are all forces within the 2-people boat system, right? And so the center of mass of the total system has to be the same because there are no external forces on the whole system. You see what I'm saying? So yes, the people may move around, which may cause the boat to move around, but from a perspective of, from physics perspective, the center mass of the system has to remain in the same position because the whole system has no external forces on it. Or if the whole thing had an external velocity, right, then you would use Newton's first law and you would say, okay, well, there's still no external forces, so the velocity of the center of mass must be unaffected even as you exchange forces within the system, right? So very powerful concept actually to think about the center of mass of a system, which is what we're doing all the time, right? Because in any distributed object, the atoms within the object are in motion and there's all kinds of internal forces being exchanged and stuff. So we're basically using this center of mass concept all the time when we're simplifying objects. So here, once again, is an elaboration of the point I was making before, right? So when you say jump off a diving board, right, you're just subject to gravity, so you know that there's something parabolic about your motion. But if you yourself are spinning head over heels and tucking your body in and extending your body, like all kinds of any different point, single part of your body may not do a parabola. But what is doing a perfect parabola here is your center of mass, right? So if we were to connect the belly button of the person in all these pictures, then that would be the part of the person that is respecting the parabola, right? Even though your head is doing all these other crazy things. Likewise, if you like throw a bomb in the air or something and something blows up in mid-flight, the pieces will go off on their own trajectory, but the center of mass of the entire system, since that explosion was an internal force, the original parabola is still respected in some way. And what way is that? It specifically is the center of mass of all the pieces afterwards will have to follow that original trajectory, once again, because the only external force is gravity on there, right? So these are just two examples of the power of knowing where the center of mass of something is. Sometimes you'll see the term center of gravity, so I just want to say a word or two about that, which is that the center of gravity and center of mass are almost interchangeable. In most situations, you can use them the same. If you have, there is a technical difference though, and the center of gravity is the central weighted average of an object with respect to a gravitational field, right? So if the gravitational field, if you're modeling it as constant, like you're near the Earth's surface and your body is pretty small compared to the rate of change of gravity, for instance, in all our problems, we pretend like G is 9.8 on the second floor of Wayland High School, the same as it is on the first floor. Well, then center of gravity, your center of gravity and your center of mass would be identical, right? But let's say you're thinking about something like the moon and the fact that the Earth's gravity pulling on the moon on the side of the moon closest to the Earth is a little bit stronger than the gravitational attraction the moon feels on the far side of the moon. Then the center of gravity of the moon will be slightly closer to Earth than the center of mass of the moon considered in isolation, right? So there is there can be a technical difference between center of gravity and center of moon, but center of gravity and center of mass, have those technical differences. But I think for everyday objects and everyday problems, you'll see those terms used interchangeably. The other useful thing about center of mass is it explains where things are stable, what the balancing point is of something. So if you take an object and like a meter stick and you want to balance it on your finger, why does it balance at the 50 centimeter? Or if it doesn't balance at the 50 centimeter, what's that telling you about your meter stick, right? It's telling you that one end is heavier than the other. And so that balance point is the center of mass. So if you hang something, for instance, like this is like some kind of pear-shaped object. See, they're using CG here for center of gravity rather than center of mass. There's a good example of it. So if you hang something, right, and it's going to swing down, where will it settle? It'll settle such that its center of mass is either above the support point if you're supporting it from below, or in this case, you're supporting it from above. It'll be below the support point. And so quick way to find the center of mass of an object is you can hang it from two different locations and then draw a line. That's what they're representing in this third picture, right? So when we hung it from P1, we drew this dotted line here, which is still on the object. And then we hung it from a different point, P2, and we draw a straight line there. And the center of mass, of course, has to be at the intersection of those 2 points. So if you have a kind of a messy object that it would be pretty difficult to actually use this formula on, this is an experimental way to find the center of mass or center of gravity very quickly. Now, whether something is stable or not. So for instance, you can balance something like if I were to hold this in the palm of my hand, as long as my hand was below the center of mass, it would balance. But of course, when I hang it from the ceiling, it also balances in that same way. But this is actually considered much more stable because if I knock it sideways, it'll come back. It'll swing around and come back to where it was. Whereas if I'm supporting it from underneath and I knock it over, it's just going to fall over and not come back. So that's the difference between something being stable and something being unstable. So let me illustrate what that has to do with center of mass. So if, we're talking about perturbations are small changes, right? So if you come and something is in sort of equilibrium and you knock it slightly or perturb it, then there's that perturbation will reveal whether you had a stable or unstable situation, right? If it's stable, it's robust under perturbation, meaning it comes back, right? It doesn't fall over. If it's unstable, then any perturbation makes it fall over and it doesn't come back. And so one quick way to analyze this is, does the perturbation cause the center of mass to get lowered or to get raised, right? We're assuming we're in a gravitational field because gravity is what's making you fall over. And the answer is, if the perturbation causes your center of mass to get lowered, then gravity will continue to lower it and it will fall. So the situation on the right. So look at the center of mass, because this object has the red extra mass at the very top. This is actually a demo we can do in class. If you remind me, I'll break it out. So this is top heavy, right? So you can certainly balance it because the center of mass is going to be above the contact point here. But if you just strike this slightly, it's going to fall over, and eventually it'll wind up looking at like picture A, and it won't come back. So letter C is an unstable equilibrium, and that is represented by the fact that this red X, the center of mass, gets lowered under any perturbation. Unlike if you start in situation A, the center of mass is pretty low, right? So this is always stable. This is why, like in certain sports or when you're designing race cars or something, they talk about how advantageous it is to have a low center of mass, is because having a low center of mass makes it harder to lower it even farther, right? So things tend to raise your center of mass, which means that gravity pulls you right back down. And so this is a stable equilibrium, because if people push you from side to side, yeah, you'll get knocked over, but you'll come back over, right? If the center of mass is neither raised nor lowered, like in picture B, then you're neither stable nor unstable, right? If the thing moves you over, you don't keep going and you don't come back, right? So it really is about what's happening to the center of mass. It's really what's telling you about your stability. So think about that next time you're on taking a bumpy ride. Why is it that you will stand with your legs far apart on a bumpy ride? Part of it is just to give yourself a wide area of support so that you can keep your center of mass above your support points, right? Because your support point goes all the way from the outside of your left foot to the outside of your right foot. But it also lowers your center of mass, right? So there are two advantages to doing that. And people do these things kind of instinctively. Like, you can think about where your center of mass is when you ride a bicycle, and why you do the things you do in those situations too. Okay, that's all I wanted to show you. I'll see you in class.